All right, welcome back, guys. I think we're gonna try to finish up 6A in this part 2 video. So if you recall, we were looking at finding the mean, the median, and the mode. And the last thing, let's see. Then we talked about how the mean is geometrically, it's like the center point, or the balancing point, where you would put the fulcrum such that you would have just as much weight on the right side as you have on the left side. And we said the mode is simply the middle value in a data set, okay? And for the mode, you have to put the data in order. And the last thing we talked about was how the mean can actually be easily affected by outliers. Okay, so but in other words, data values that are not typical of the data set. And the example we looked at was if we were talking about yearly income of individuals in this class, we could find the mean and the median, and they would probably be relatively close together. But then if we had somebody super rich like Elon Musk or some other billionaire, and we added that to the mix, then that would cause the median would essentially more or less stay the same, but the mean would get raised up so high that it would make it look like we were all millionaires, because the mean would probably become several $1 million. All right, so now I want to talk about shapes of distributions. Okay, and when I say distribution, guys, what I am referring to is if you have a data set, how is it distributed? Okay, where does most of the data lie? Does it lie in the middle, close to the mean? Does it lie in the lower values or in the upper values? And the shape of a distribution really refers to what does the histogram look like. So if you had a data set, you would make a frequency table and then create a histogram, kind of like this one here, or this one up here, okay, when we're talking about these female Academy Award winning actors, this is a histogram, but it has a shape, okay, and what's common is that when we're talking about shapes of these distributions, we tend to kind of, instead of thinking about the shape, it's including like these jagged or abrupt bars, we think about it as a smooth curve. So for example, we could sort of maybe give it a shape like this, okay, try to even out all the irregularities, something like that, okay, so kind of a smooth curve. So when we start seeing examples of these distributions, they're going to be smooth curves. But just remember, they're based essentially on like the histograms that result from organizing your data in a data set. All right. Okay, so there's really 3 types that we're going to look at. One is symmetric, okay? So that just means that the left half is a mirror image of the right half. So an example of that would be this one right here. Okay, this would be a symmetric distribution. And what we're talking about here is height of women, okay? And then the second one we're going to look at is a distribution that's left skewed. So what this means is if the values are more spread out on the left side, or in other words, if it has a left tail. Okay, so I'll give you an example. I'll draw you an example. Okay, so it might look something like this. The peak would be on the right-hand side. Or in other words, most of the data values would be over here on the right. You would still have data values over here to the left, but there wouldn't be as many of them. Okay, and then a right skewed or right-tailed distribution is just the opposite. You have most of your data on the left, and then you have a tail or less data values over here on the right. Okay, So like remember these result from histograms. So like the bins or the bars over in this area, the frequencies would be very low. Okay, an example would be like this one right here. This is a right skewed distribution. And the reason was because there's fewer older female Academy Award winning actors. And hold on just a minute, guys. My computer froze again. Okay. And we also discussed it's right skewed or right tailed because most of the data lies on the left, or in other words, it's the younger actresses that typically win the awards, those in their 20s, 30s, and maybe into 40s. Okay. All right, so let's get some practice. It says, describe the shape of the distributions below. How many peaks? Well, this first one, as I mentioned previously, this is a symmetric distribution. In other words, if I were to draw a line kind of in the middle or right where that peak is, and I have mirror images on both sides of this. Okay, the left-hand side is a mirror reflection about this vertical line of the right-hand side. So we would call this a symmetric distribution. We're going to talk more about this type of distribution when we get to I believe it's 6C, the last section of chapter 6 that we'll cover. And there's only one peak. The peak, guys, typically corresponds to the wherever the mean, median, and mode lie. Okay, so the mean, or the center of this distribution, because it is symmetric, is going to lie right here in the middle. Also, the mode, if it has one, is going to be here in the middle, and the median would be right here in the middle. Okay. What about this next one? This one I like. It's interesting. So what we're measuring here is time spent watching television. Okay, so we would expect to see some variation. What I notice here is that this one actually has two peaks. And you would expect that because we're including both men and women in this data set. So we would expect to see one peak for men and another peak for women. Okay, and you can see that the peak for men is further to the right. This would suggest that men, on average, watch more TV than women. Okay, but interestingly, this is also a symmetric distribution because if you draw a line, vertical line right down the middle, the left-hand side is a mirror reflection of the right-hand side. So this too is a symmetric distribution, okay? But it has two peaks. Okay. Now, the mean and the median are probably going to still be here, right here in the center. Okay. However, the mode, and this one might have two modes. The modes would probably be one maybe right here, corresponding to that peak for women, and then it might have another mode over here corresponding to that peak for men. All right, what about number 3? This one's interesting. This one's kind of a cool one as well. The distribution, let's see, weekly sales throughout the year at a retail clothing store for children. Okay, so what we have on the horizontal axis is the time or the month of the year, and what we see on the vertical axis is the actual number of sales. It's sort of like the frequency, but this is really more like a time series chart than it is reflective of like a histogram. But anyway, you can see that it has 3 peaks, and these peaks correspond to peak spending or peak buying seasons for children. Okay, so one right here, kind of in end of February into March for maybe spring sales. One right here at the end of summer for back to school shopping, and then one right here toward the end of the year that would correspond to holiday spending. Okay, but this one is not symmetric, but it does have 3 peaks. So it could potentially have 3 modes. The data set, that is. Okay. All right. Oh, and there's one more here. This one's kind of cool too. This one, it says the number of people with particular last digits from 0 to 9 in their social security numbers. Okay. So think about a person's social security number. You can sort of think about them as being random, although they're not actually random, but you could look at the very last digit as being random. So like if you just randomly picked somebody and asked them what the last digit in their social security number was, that's essentially going to be like picking a random number between 0 through 9. Okay? And so because of that, if we can look at those numbers as being random, then the probability of there being a 0 or 1 or a 2 all the way to 9 would be essentially equal. You're just as likely to pick somebody that has the last digit of their social security number be a 0, or be a 7, or be a 9, or be a 2. And so because of that, the shape of this distribution, guys, would actually be horizontal. And what this means is that for each of these numbers, you are no more likely to select one or have one be somebody's last digit in the social security number as you are another. Okay? And so that's why this is actually called a uniform distribution. I'll just put this in the notes. Okay? Uniform distribution. And it doesn't have any peaks because it's uniform. Okay? So there is not going to be a value occurring more than once. The mean and the median would be right here in the middle. That would actually be the same value, probably like 4.5, because that's halfway between 0 and 9. It wouldn't have much significance, though, because you can't have a last number in your social security number be 4.5. Okay. But anyway, this actually is also a symmetric distribution, because if you draw a vertical line here, okay, the left side is a mirror image of the right side. So this uniform distribution is symmetric. All right. So let's look at some other examples. These are some other examples of symmetry. Okay, each of these distributions, they're all symmetric, and you can see where that line of symmetry is. It's right in the middle. Okay. One thing we're going to, well, let's see here. Talk about it. Yeah, we'll actually talk about it in just a second. We'll definitely talk about it in 6b, is variation or skewness. Variation basically means how spread out is the data set, or how much does the data vary. There's actually more variation in this third distribution here than there is in this first distribution. Okay. But these are some other examples of distributions that exhibit symmetry. Now remember, the shapes of these distributions are really just coming from histograms. So if you could think about, like something like this, coming, having all these bars, but when you kind of connect the bars with a smooth curve, you end up getting something that has this shape. So, alright, so let's talk about the three we mentioned earlier. A left skewed distribution is going to look like this. In other words, most of the data is going to be over here to the right, and the data on the left is going to be more spread out, and there's going to be less of it. And I'll also note, with a left skewed distribution, you're going to notice that the mean is going to be to the left of the median, because the outliers are going to be to the left. Okay? The outliers are going to be the lower values. That's what causes it to get skewed to the left. Okay, so it pulls the mean to the left. Remember how those outliers affect the mean. The median is going to stay closer to the middle, and then the mode is going to correspond to wherever that peak is. Now contrast this with a right skew distribution. So that means you're going to your outliers are going to be more toward the right. That's what pulls it or skews it to the right and gives it this right tail. But the majority of your values are going to be to the left, so that's where you see your peak and your corresponding mode. But because your outliers are toward the right, that's going to pull that mean to the right of the median. So think about that example, that annual salary example, and Elon Musk or some other billionaire. That's going to skew the data or pull that mean to the right. And then in a perfectly symmetric distribution, the mean, median, and the mode are all going to be right in the center, roughly in the center. Okay. So, in skewed distributions, the median is going to be a better measure of the center of the distribution. Okay, remember, because when we were talking about Elon Musk, if we account for his annual income, and that makes us all look like millionaires, and that's not very characteristic of the data set, because we're not millionaires, are we? Okay. So the median would be a better measure. The median would be really close to what the old mean was, okay, before we took Elon Musk's or some other billionaire's annual salary into consideration. All right, and then when a distribution is symmetric and single peaked, like this one right here, both the mean and the median are going to be good measures. Okay? That's the central, wherever the center of that distribution is. All right, so now let's talk about variation. So variation just means how spread out is the data. Okay? So if the data is not very spread out, or the range in the data is not very wide, then you're going to get a distribution that looks like this. And we say that the distribution or the data has low variation. Okay? When there's moderate variation, then it's going to be spread out more, like in this example. And then when there's high variation, that means it's spread out even more, and you get a really stretched out histogram, okay, or distribution. We're going to discuss this more in detail in 6b. All right. Before we do example 2, let's actually look at example 3, or this last one here. So which has the most to least variation? Okay, so we've got, let's see, we actually have four distributions here. You can think about these just being the continuous shapes of histograms. So which one has the most? Okay, well, it would be the one that's spread out the most, or the widest, so it's going to be D, okay, the one in yellow or gold here. So most would be D, and then after that, I think would be C, okay, because I think it's the one that's spread out the most after D, okay. And then would be A, and then finally B has the least. In other words, it is the most horizontally compressed. Okay, it's the one that's least spread out. All right, now let's look at this last example. This is a good one. I like it because you have to think critically. It says, would you expect the symmetry and variation to differ between the times in the Olympic marathon versus times in the New York marathon? Okay. And so, of course, you know, in a live class, I ask my students and we talk about it. So we talk about the nature of these two different races. So first of all, we need to know that a marathon is just a race. It's roughly 26.2 miles. Okay, its history is found in ancient Greece. But anyway, so it's a race. It's about 26 miles long. Okay. Now, what would you think the difference would be? So we're talking about the times. Okay, so how fast can a person run this race? How fast can they run 26.2 miles? Well, you wouldn't expect it to be very fast. So let's talk about the differences in these two races. So the New York Marathon, or think about the Little Rock Marathon versus the Olympic Marathon. Okay. Well, with the New York Marathon or the Little Rock Marathon, guys, you don't necessarily have to be an elite athlete to run it. Okay, you just have to pay the registration fee, show up, and run it. Now, there are also elite athletes that do run in these, though. Okay, that's one of the ways they make a living is by running in these marathons around the world. Okay, so think about the Little Rock Marathon. You may even know somebody that's running the Little Rock Marathon. Their time's probably not going to be very fast. It's, might be 10 hours, 10 or 11 hours. The fastest in the world can run it in a little over 2 hours, roughly 2 hours. And then you're going to have a whole bunch of people that are finishing somewhere in between for the New York or Little Rock Marathon. Okay, so I would venture to say that it is probably symmetric. Those times probably are symmetric. Okay, if the horizontal axis represents the actual time, and the vertical axis represents the frequency, or in other words, the number of runners, okay, you're going to have very few runners finishing down here in the low time range in 2 or 3 hours, but at the same time you're going to have very few people finishing in like 11 or 12 hours. The majority of the people are probably going to finish somewhere in between. Okay. So this would be like for the New York. We could say maybe down here is 2 hours, or close to 2 hours, and then maybe way up here is like, I don't know, I'll say 13 or 14 hours. Okay. Now let's think about the Olympic Marathon. Okay. So we'll still have the same thing, time, and then up here we'll still have the frequency, or the number of runners. However, to be able to run in the Olympic Marathon, guys, you have to be an elite athlete. It's a race that you have to qualify for. In fact, if you can't run under 3 hours, you're not even going to qualify. You have to be running in the low 2s to even qualify. So this distribution, it probably will also be symmetric, but it's not going to be spread out very much. Okay, this might be 2 hours, which is like the world record. Actually, it's going to be really narrow. It's going to be a lot narrower than I even drew it. Let's say, I don't know, let's say here's like 2.5 and then here's 3 hours for the sake of argument. Okay. Let's say the person that wins it is going to run it close to 2 hours, and then maybe these people qualified, but they just had really poor performances and they ran like in a high 2 hours range. And then the majority are still going to run somewhere in between. Okay. So this one's still going to be symmetric as well, but it's going to be a lot narrower. Okay, there's going to be a lot less variation. And then the times associated with the New York or Little Rock Marathon are going to have significantly more variation. Okay, so hopefully that makes sense to you, the difference there between those two distribution of times. Alright guys, so that actually does it for 6A. So in the next video, 6B, we're going to be talking about, okay, well we know how to find like the center of a data set or the center of a distribution. We know how to find the median, the mode, the mean. And we've talked about this idea of variation. How much do the data values vary, or how spread out are they? But in 6B, we're actually going to look at a way to quantify that. Okay? Because in math, we like to use numbers and not words. We don't like to say, this data set is pretty varied. Okay, what does that mean? Okay, if you can't assign a number to it, then you can't really measure it. And so we're going to look at how we can actually measure it, measure that variation. All right, so I'll see you there.